Alrighty guys, so this is just going to be part of the pre-lesson content for you guys to go through, just so that again we can go through the questions in class with all the learning being done beforehand in this pre-recorded video lesson. So if you guys have any questions, feel free to message the chat and I'll get back to you guys. So we're covering 2 weeks of content and I'll be doing it in parts and stitching them together, so it might feel a little janky, but hopefully this video is helpful for you guys. So we're looking at now essentially probability that was covered in the advanced maths course. I'm not sure if you guys have covered it at school yet, but it's to do with continuous distributions. It's to do with expected values, variance, and all of that stuff. So the first bit of content that I'll be going through, the week 5 content, is kind of the preface, that's the word, preface for the continuous distribution. So this content specifically in week 5 is still technically discrete. And that will make sense as we go through it. It's not really too important that you understand the connection between the two, but it will be handy, of course, to know how it kind of flows from this week's content to the next. And I'll get into that. And later on, there's a good question as well that we'll be covering that kind of draws that bridge between the two worlds of discrete and continuous. But anyway, let's get into it. So the first concept we'll be looking at is a Bernoulli trial. This isn't particularly important, to be honest. All a Bernoulli trial is, it's basically a way of looking at events as binary. So for example, and by binary I mean either it happens or it doesn't happen, or in other words, there's two outcomes. So for example, if you flip a coin, you can either get a head or not a head. Or when you roll a die, although there's multiple outcomes with a die, we can break that into, or we can boil it down to a binary event by saying, okay, do we roll a 6 or do we not roll a 6? Do we score a goal or do we not score a goal? So it's not about how many possibilities there are necessarily, but it's about how we frame it. And usually when we look at, Bernoulli trials, we denote the success with a P, that's just a notation, and then the failure with either 1 minus P or Q. And the other important thing to note is that trials are independent. So if I do one experiment, one trial, so if I flip a coin, for example, that won't impact the next trial. So it's kind of intuitive in that sense, but it's actually an important feature of the Bernoulli trial, which helps to do the next thing, which will be binomial trials. And we'll get into that a little bit later. But here's some key information on Bernoulli random variables, and hopefully you've come across this in the advanced maths course. So this is a fancy way of kind of writing, okay, if I have a success, the probability, so that's when little x is equal to 1, the probability of that success is little p, and if I have a failure, so this is 0, then the probability of that failure is 1 minus p or q. Then I've got the expected value, so this is e to the x, so the expected value of that random variable, it's actually p, and then the variance is p times 1 minus p, or in other words, pq. So this we won't really be looking too far into, to be honest. The variance and expected value will look more so when we look at binomial probability. Okay, let's quickly look through this, decide whether each statement could represent a Bernoulli trial. And just a heads up, we'll be only looking at the examples during this video. In class, you'll be going through the question. So that's why it's really important that you watch this video and look through all the examples and try them yourself. In fact, that way, when you get into class on Friday, you can just literally go through the questions. Okay, decide whether each of them are Bernoulli trial or not. You either pass or fail an exam. Yep, that's Bernoulli because it's either one or the other. You can either buy a particular brand of phone or not buy it. That's a Bernoulli trial too. So you'll note how, hold on, let me just go on do not disturb. You'll note how although we have multiple brands out there, because we're reframing it as we either buy one brand or not, or the other, sorry, we either buy one brand or we don't buy that brand, it becomes a Bernoulli trial. Okay, you can either walk to school, ride your bike, or catch the bus. So this is multiple possibilities. So that's not a Bernoulli. We could frame it as a Bernoulli by saying you either walk or you don't. And then part D, you can either get the job that you applied for or not get that job. So that's one or the other. That's a Bernoulli trial as well. Okay, these are the questions. This question you go through in class. And now let's have a look at binomial probability. So this is more so the focus of the Extension 1 course. It looks complicated. It's not too difficult, and we'll see as we do the examples. So I won't spend too much on this because it's easier to understand through the example. But basically, a binomial probability is multiple Bernoulli trials. We're doing multiple trials, and each trial is a Bernoulli trial. So that will make more sense as we do the question. And each of the trials is identical, and each has a success probability of P. Again, just this is the notation for success. And then all trials are independent. Again, a critical feature of binomial probability. And this is how it's set up. It's basically N is the total number of trials. X is kind of the number of successes we're looking for, or the number of a particular outcome that we're looking for. And then this is the probability of success, and this is the probability of failure. Now you'll see that it's quite reminiscent of perms and coms, and that will make sense once we look at this example. And I'll take us through that kind of connection with combinations. So the probability of any particular egg being cracked in a carton containing a dozen eggs is 0.05. So I'm going to say that this is the probability of success. And again, it depends on how we frame the question. So if we are wanting to find the number of cracked eggs, then this is the success, probability of success or probability of cracking an egg. It doesn't really matter as long as you know which variable you've assigned to what, or what probability you're focusing on. It doesn't matter that I've said that P is 0.05, and that'll make sense a little bit later. So don't get too caught up in, trying to, put a certain variable as a certain value. Find the probability that exactly 3 eggs are cracked, stating your answer correct at 3 decimal places. So let's kind of break this down. So we've got a carton of a dozen eggs. So meaning we have 12 draws or 12 trials. And each trial, each time we pick an egg, has the same probability of being cracked, which is 0.05. So this is my probability of success. And I'll say N is 12 down here. And we want it such that we have exactly 3 eggs cracked. And here's where the combinations comes in. Because we're picking 12 eggs, any 3 of those could be cracked. So it could be the first 3, it could be the last 3, it could be the middle 3, or any combination of the dozen eggs could be cracked. So the way that we pick the cracked eggs is 12C3, yeah? And this is the probability of it not being cracked. So what we want is 9 non-cracked eggs, and we want 3 cracked eggs. And this is what I mean by we don't have to get too caught up on what the P value, what P should be, what Q should be. If you think about it in this way, in a combinations way, and actually understand what you're doing, you don't have to worry about the formula. We've essentially just, not derived the formula, but we've essentially just, come up with a formula, and we haven't had to go back and plug certain things in. So again, what I'll say, I'll repeat myself. So out of the 12 eggs that we have, we want 3 to be cracked, meaning we want 9 to not be cracked. This is the probability of an egg not being cracked, and we want 9 of them. And this is the probability of it being cracked, and we want 3 of them. And if we put this into our calculator, this will come out as 0.017332, but we want it to 3 decimal places. So this is it to 3 decimal places. Okay, hopefully that's making some sense. Let's have a look at this next example. A particular medical test correctly identifies whether or not a person has an illness 98% of the time. If 10 people are tested, find the following probabilities correct to 3 decimal places. So what I'm going to say, so there's 10 people, so 10 trials, and we're testing each of them. And so eventually we'll test 10, so 10 trials. And I'm going to say this probability of success. So this is the probability that we correctly identify a person to be sick is 0.98. And so question A is asking that no people are incorrectly diagnosed. Or in other words, we correctly, a particular medical test correctly identifies whether or not a person has an illness 98% of the time. So I just want to make sure I get this right. So no person is incorrectly diagnosed, meaning that we want to correctly diagnose all 10. So the probability of correctly diagnosing all 10 is 0.98. And we want all 10 to be correctly diagnosed. And for incorrectly diagnosed, the probability is 0.02, and we want 0 people incorrectly diagnosed. And so if we put this into our calculator, this will be 0.817072869, and this is to 3 decimal places, 0.817. Okay, so this is the probability that everyone is correctly diagnosed, or in other words, no people are incorrectly diagnosed. So kind of a tricky wording of the question there. Now, part B, at least one person is incorrectly diagnosed. So this is the probability that no one is incorrectly diagnosed, or in other words, everyone is correctly diagnosed. Part B is asking that at least one person is incorrectly diagnosed. So to do that, to get that probability, we'll do 1 minus that everyone is correctly diagnosed / no one is incorrectly diagnosed. So that's just the previous probability subtracted from 1, which would be this, and this would give us, to 3 decimal places, 0.183. Okay, here's the next example. This one's a little bit trickier. So Arib and Rafid make shirts for a living. Arib works more slowly but more accurately, making 20 shirts a day, of which 2% are defective. Rafid works faster, making 30 shirts a day, of which 4% are defective. If they send out their shirts in randomly mixed parcels of 30 shirts, what is the probability that no more than 2 shirts in a box are defective? So this question is a little bit tricky, but basically what this is saying is that the number of trials we have is 30. Yeah, so N is 30, because in a box of 30, that's the kind of package that we're going to be receiving, and we'll be taking out, each shirt. So each time we take out a shirt is a trial, and we're looking such that we're wanting the probability such that there's no more than 2 shirts that are in the box that are defective. And you can kind of imagine that this is how manufacturing works. So they would want certain quality assurances. If they have a bulk, if they make them in bulk, there's guaranteed some defective items, and so they want to kind of get an estimate, maybe for corporate or maybe for finance, to go, okay, like the chances of there being, less than 2 defective in units in this batch are quite high. So meaning that, we shouldn't have too many defective units. We should be able to sell all of them. And we have a fairly high confidence that's the case. So this is kind of a real world problem in that sense. But let's break this down a little bit. We don't have a direct probability for a shirt being defective. So instead, what's happening is that we've got 2 sources of people making shirts, and they have different defective rates. But what we can do is we can come up with an average for what the defective rate is. And in this case, because they're making different amounts of shirts, we have to do a weighted average. So in total, if they make 50 shirts, Arib is making 20 of them. And his defective rate is less, it's 2%. Rafid is making more shirts, he's making 30. So, his like mistakes will have a higher weighting because more of them are his shirt, and he has a 4% defective rate. And if we work this out, this is 0.32. So the probability that in any batch, the probability of a shirt being defective is 0.032, given that we've mixed their shirts together. Okay, so we are wanting to know such that, and I'm going to use some notation here. So I'm going to let X be the number of defective shirts so that we can kind of have a look at that random variable notation. So what I want is this probability that no more than 2 are defective. So I want 2 or less. And this I can break into there being no defective shirts, there being 1 defective shirt, and there being 2 defective shirts. So 2 or less is the same as 0, 1, or 2 shirts being defective. So let's have a look at each of these probabilities. So when we have 0 defective shirts, out of the 30, we want all of them, or we want none of them to be defective. So I'm going to say this is my probability of it being defective, and I want none of them to be defective. So again, I'm not really thinking about the formula. I'm not thinking about what's P, what's Q. I'm saying, okay, this is the probability of it being defective, and I want 0 of them to be defective. To find the probability of it not being defective, I subtract 0.032 from 1, which gives me 0.968. And I want all 30 of these to be not defective. Okay, now if I want 1 shirt out of the 30, and remember again, we're using the combinations because any of the 30 could be not defective. So out of the 30, I want 1 of them to be defective. So I want 29 to not be defective, and I want 1 to be defective. And then finally, I want 2 defective. So that probability, let me just double check this is recording because that would be really annoying if it wasn't. And this is 2 being defective. If I put this into the calculator, which it would be quite annoying to do, this would come out as approximately 0.93. All right, so that's that example. And you guys will do all these questions in class. And then the final thing that I'll talk through for the week 5 content before we jump to the week 6 content is a binomial distribution. So this is effectively visualizing what these binomial distributions look like. Now, the binomial distribution is a discrete distribution, and that's because we can have only whole number outcomes. And that's because we're looking at trials, right? We're looking at, okay, I'm looking at 30 shirts, I'm looking at 20 iPhones or what have you. It has to be whole numbers because we're looking at trials of things, and you can't have 1.5 trials. And so if we look at the distribution, this is how we would denote the distribution. So we're saying, okay, the X, we have a random variable X, and this is a binomial distribution. That's what this is saying. And then later we'll visualize what this looks like in the next slide. But here, N is the number of trials and P is the probability of a success. And this is also some important information. We've got the expected value is the number of trials times the probability of a success. The variance is N times P times Q. So number of trials times success times failure. So pretty neat formula. Now, if you're going to do actuarial studies, you'll be looking at some much more complex distributions with some much more complex expected values and variances. So expected value is kind of like the average if you don't know, and variance is like how spread out the numbers are. And if you do actuarial, you'll have this thing called the orange book that has all of these distributions in there for you, so you don't have to memorize them. It's like a formula sheet on steroids. But let's have a look at the way these binomial distributions look. And it looks complicated, but it's not. Let's talk through it. So let's have a look at this binomial distribution. So we're saying we've got 10 trials and the probability of success is 0.25. Now, what each of these are representing is the probability of the number of successes. So you can see that this is the highest bar. So let's focus on this one. So this bar is describing the probability of having 2 successes. So that's around 0.3. So if we had a distribution that was, 10 trials, let's say we're picking, like out of 10 shirts, let's say it's shirts again, the probability of shirt being defective is 0.25. Having 2 defective shirts would be the most, common or the most likely outcome, which would have a probability of around 0.3. Having 0 defective or 0 in this probability distribution, 0 successes, is also a bit low. And then it increases up to and then drops off again. Now, what you'll notice is that they're more skewed towards the left, these are the more popular ones. And that's because the probability of success is relatively low, which is why you would have, it would be hard to get a lot of successes, right? So if your chance of success is only 0.25, it would be hard to get 8 successes. Not impossible, just have a very low probability. But at the same time, it's kind of unlikely that you would have no successes. You would have some successes, but very low number. On the flip side, if your probability of success is quite high, it would be pretty hard to get not many successes. So this could be, I'm trying to think, maybe the probability of rain in a week. So if the question could be, or the scenario could be, what the probability that it rains at least once in a week is 0.75. And you're looking at 10 weeks, the chances of it not raining at all is extremely low because there's a high probability of success. That's why it's skewed this way, and you have a more higher chance of having more successes. So that's why in this case, 8, for example, is the highest. But that's why, for example, this one is symmetrical, because you have an even chance of getting 0.5, and then this is where the expected value actually comes in. And the expected value in this case is 10 times 0.5, which would give us 5. And in this case, it would be 2.5. So it would lie somewhere in between the expected value. So not always the most probabilistic outcome, the expected value, but hopefully this helps make sense of how these distributions are coming about. Now let's quickly talk through these kind of theory points. So I said before it's skewed to the left, but that's actually not the technical way to describe this. This is actually just skewed to the right. And remember, when we looked at this, the skew side depends on where the tail of the distribution is. In this case, it's more towards, the tail would be towards the right. In this case, the tail would be towards the left, meaning skewed to the left or negatively skewed. In this case, skewed to the right or positively skewed. Okay, so yeah, as n increases, the graph clusters more tightly about the mode. So in this case, you would, cluster more around here, but retains the same shape. And when we look at normal distributions, that's like having an infinite number of outcomes. And that's why, we would fill up all of the spaces effectively to get a continuous, smooth distribution. Actually, a normal distribution is more like this one because it's symmetrical. And we fill up all of the spaces to get a continuous distribution. And we'll talk more about that later. But keep this in mind for the week 6 content, which is the normal distributions, because it's essentially pushing the number of bins that we have to infinity. That's how we get a smooth distribution, and which is also why we look at ranges and not specific values when looking at continuous distributions. Okay, let's very quickly have a look through these examples. These are a little trickier, and hopefully it doesn't take too long for us to go through, but let's have a read through. A binomial random variable has parameters n is equal to 20 and p is equal to 0.1. Find the mean, variance, and standard deviation. So let's actually write down the critical formulas. So expected value is n times p, and then the variance is n times p times q. So if we're looking at the mean, that's just the expected value. So in this case, the mean, and I'm going to denote it as mu, just so that we can get used to some more notation. It's just going to be n times p, which is 2. The variance, and I'm going to use this notation. So I think sigma, I can't remember what this thingy is called, this Greek letter. This is going to be n times p times q. So it's going to be 20 times 0.1 times 0.9. And this is 1.8. And if you remember, the standard deviation is just the square root of variance. So we would have square root of 1.8, which is 1.34. Okay. And that is the answer to part A. Let me grab this and put it down here. All right, part B. What is the probability of getting the mean when the experiment is run? So what we're looking for is 2 successes. That's pretty much what this question is asking. So we have 20 trials. The probability of failure is 0.9, and we want 18 of those. And then the probability of success is 0.2, and we want 2 of those. So if I put that into the calculator, I think I may have the wrong answer here, but let's just go with what I have in my solutions. If you guys put this into the calculator and get something else, that's probably the right answer. But in my answers, I've got 0.285. I think there's a... Oh, sorry. This should not be 0.2. This should be 0.1. So this is the right answer. So this, remember, is a probability of success. I was putting in 0.2 for some reason. But yeah, this is the answer to part B. Now, part C, what is the probability that the result is within 1 standard deviation of the mean? So now we're kind of getting closer to the normal distribution content. So, and once we get to that, that'll also make sense why that's the case. So results within 1 standard deviation of the mean. So let's have a look. Our mean is 2. To be within 1 standard deviation of the mean, we want to go down 1 standard deviation, and we want to go up 1 standard deviation. So if you think about this, the mean is here at 2. We want to go up 1 standard deviation and figure out what that is. So that would be 3.34. And then we want to go back 1 standard deviation or down 1 standard deviation, and that would be 0.66. And essentially what we want to know is what is the probability that we get within one standard deviation. And the thing is, because this is a discrete distribution, we can't find the probability of 0.66 and 0.34. We don't have fractional numbers to work with. So instead, we're going to approximate this to the closest thing that makes sense. So we don't want to go down to 0 because then that's going more than 1 standard deviation. So we'll pull it back to 1, and we'll pull this down to 3. And this will give us an approximation. I'm just going with equals because, we can't actually get 0.66 and 3.34. But this will give us a sense of, a rough sense of what 1 standard deviation will look like, because we can't get exactly 1 standard deviation. And if we want the probability of the outcomes or successes being between 1 and 3, that's the same as having the successes, 1 success, 2 successes, and 3 successes. And the way to figure this out is very similar to the previous question that we did. So if we want 1 success out of the 20, we need 19 failures, and I'm saying success and failure, but they could be framed a different way. But I want 19 of the 0.9, and I want 1 of the 0.1. So in this case, the success is 0.1. But yeah, like I don't like to frame it that way all the time because it gets a little bit confusing. I like to think about it as how many of those that I want. So if I want 2, I want 18 of these, and I want 2 of these. And if I want 3, I want 17 of 0.9, and then I want 3 successes. And if I put this into the calculator to 3 decimal places, this would be 0.745. Okay, here's the next example. And this one is a little trickier. I'm going to quickly go through this one. And if you need to play it back, please do. But this will actually take us to the end of the content that you guys need to learn for this week. But let's look at part A. Find the mean and standard deviation. So we start off nice and easy. So the mean, we get 100 times the probability of success. This will give us 20. And then we want the standard deviation. So this is going to be, and if you remember, we don't have a formula specifically for standard deviation, but we have one for variance. This is going to be 100 times 105 times, so the probability of success times the probability of failure. And if we want to get the standard deviation, I just take the square root. So this is going to be square root of all of this stuff. And this is going to come out as 4. So my standard deviation is 4. All right, let's have a look at part B. Keeping P is equal to 1 on 5, what would n need to be increased to so that the standard deviation is less than 1% of the number of n trials? So this is a very complicated sounding question, and it's somewhat connected to the real world stuff. So if you think back to our manufacturing plant example again, we want, certain assurances that our batch is going to be, have a certain level of quality. Or, we could be looking at statistics of something. So if someone says, the probability that this medication works based on our trial is, 90%, but we only tested on 10 people, there's a lot of variability. So for it to have a 90% success rate would mean that it worked on 9 out of 10 people. But what if in another trial it worked on just 5 out of 10 people? There's very much that probability, that chance, right? So the smaller the sample size that you have, the more variability that you have, the more variance that you have. So that's why if you increase the number of trials or the number of elements in your trial, so instead of having 10 patients that you test, your cure on or your vaccination on, if you have, say, 1,000 and you get a certain result, that's much more reliable because it has much less variance. So that's essentially what this question is getting at. So we're saying keeping P is equal to 1 on 5, what would n need to be to increase to so that the standard deviation is less than 1% of n trials? So this question isn't exactly what I just described, but it's kind of along the same lines. So let's have a look. We want our standard deviation. So our standard deviation, in this case, we don't know what n is. Our p-value is, I'm going to write it as a decimal, 0.2, and our q-value is 0.8. And we want this to be less than 1% of n. And what I'll do is I'll simplify and I'll square both sides. So I get 0.69 is less than 0.001 n. And the reason I can square both sides in this case is because both sides are positive. So that's why it's okay for me to square. If I tidy this up by multiplying everything by 1,000 or maybe 10,000, sorry, I'm in a bit of a rush here. So this should be n squared. But the point is I want to get it to this equation here. So I'm multiplying each side. Let's actually double check that by 1, 2, 3, 4. Yeah, 10,000. And this is the equation that I get. And in this case, I've moved everything to the right-hand side as well. And so this is the quadratic inequality that I have. Now, to solve a quadratic inequality, I need to factorize. So I get n on the outside, then n minus 1600. And I want this to be greater than 0. And remember, to solve quadratic inequalities, I need to draw a quick sketch. So this is 0, this is 1600. And I want it greater than 0. So there's two options. One is greater than 1600 or less than 0, but I can't have negative trials. So the only number that makes sense is greater than 1600. So if I have more than 1600, my standard deviation will be such that it's 1%. It will be less than 1% of the number of trials. So it will be, my standard deviation would be, in this case, 160, I think. 160? No, 16. But anyway, let's keep moving. Keeping n is 100, so that's how you do part B. Part C is a similar question. Keeping n is equal to 100, what must P be decreased to so that the standard deviation is less than 1? Okay, and this is similar to the example that I was giving. We want such a high probability of success that there's low variability. And in a similar way, we figure out the standard deviation, which is going to be 100. This time we're keeping the n value times p, which we don't have in this case, and then times q. But q, we don't want to introduce a new variable because then we can't solve the equation. So I'm going to go with what q actually is, which is 1 minus p. And we want this to be less than 1, our standard deviation to be less than 1. So what we want to do is square both sides. And again, the reason we can do this is because both sides are positive. So if I square both sides, this is what I get. And then what I'll be doing is expanding this out. So I have 100p minus 100p squared. And then I'll take the 1 from the right-hand side across to the left-hand side. So this is the equation that I have to solve. And what I'll do is I'll actually move everything to the right-hand side so that I don't have to deal with a negative leading term. And then this is what I have. What I get is P is less than 0.01 or P is greater than 0.9899. So either way will give me a very tight tolerance. And for this one, I do need to specify that it needs to be greater than 0 because then otherwise it wouldn't work. But we want to either be very sure that this is going to work or we want to be very sure that it's not going to work. Either way, the standard deviation will be very small. And that's how you do part C. And that's it for the first half of the recording.